if you would arrive during Shabbat, there is Mm-hmm.
Good afternoon, everyone. We apologize for the delay. We were having some minor technical issues trying to transmit the screen over. So today we are going to have Thomas Rose here. He has a BA in Prehistory and Science-Based Archaeology from Tübingen University and a Bachelor of Science and Master of Science in Geoscience from the Goethe Institute from Frankfurt. And he's also the coordinator and organizer of young researchers in archaeometry. You can find the link for that interesting project in the description of this video. And today he's going to talk about experimental archaeology and archaeometry. And Thomas, welcome. We are very glad to have you here today.
Thank you.
Okay. Hope you can hear it all. So we are going to start here. Thomas, welcome. And you can start whenever you want.
Yeah. Can the people hear me if the screen is not working?
I guess so. Can you
Okay.
all hear it? If you can type in some feedback on the chat. Yeah, I can hear it. I'm checking on the video here.
Okay,
Yeah.
good.
Okay.
Then we start, yeah. So, good afternoon, everyone. Yeah, thanks a lot for the possibility to present in this webinar series. And today will be a bit more theoretical. There won't be that much images. And it's really archaeology meeting science. So it's not so much about archaeometry, but more about what other disciplines and today experimental archaeology can contribute for archaeometry and how they can profit from each other. And Sergio, the next slide. Before we start, we should ask ourselves, what is an experiment? I mean, experimental archaeology, experiment is in there. In sciences, we do experiments all the time. So what actually is an experiment? And next, in the Oxford Learner's Dictionaries, they define it as a scientific test that is done in order to study what happens and to gain new knowledge. So something is happening during an experiment, we want to know what it is and want to study it, and we will gain new knowledge. Next, on Wikipedia, it's a bit longer. It says it's an experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. Experiments vary greatly in goal and scale, but always rely on a repeatable procedure and logical analysis of the results. There also exist natural experimental studies. So what we learn here about an experiment and the next is that some kind of procedure is carried out which is based on a hypothesis. So somehow an experiment requires a hypothesis, and it provides insight into cause and effect. So this is what happens, and we want to know what is happening, and we have to manipulate a particular factor, whatever this means. We will see it in some minutes. And an experiment is also always repeatable in its procedure, and the results will be analyzed logically. So next. Basically, everything can be an experiment. Next, I'm very sorry, Sergio, I'm working with a lot of...
Yeah, we are kind of collaborating together, and we have a little bit delay between the transition of the slides. We apologize.
Yeah. Okay, so on the next slide, I want to point out some other thing. And on Wikipedia, in the Wikipedia definition, it also says experiments vary greatly in goal and scale. So next, I don't know if you can hear my spacebar. So it seems like an experiment is not exactly an experiment, or there are different kind of experiments. Who knows? So on the next slide, we can see the first type of experiment, and now it's always for each type will be one animation. So the first type of experiment is the experiment we probably think about when we are thinking about experiments as a person with non-scientific background. These are lab experiments. These are people who are sitting in the lab in whichever kind of discipline, natural sciences, psychology, sociology, pharmacy, lab experiments are defined by a control group which is there, and we are manipulating one factor and are observing another one. So we have one dependent variable and we have an independent variable. The independent variable we are changing, and we have a look what happens on the dependent variable, how it's changing when we are changing the other one. And everything happens in a controlled environment. In a chemistry lab, it's always 20 or 25 degrees Celsius, for instance, because we need to have stable conditions to have a confined environment and rule out that any changes in the temperature might cause effects we don't want to have, or maybe we want to have, but not in this case, because we are, for instance, testing for the rotation speed of our stirrer or something like this to simulate movement in a liquid. So the next kind of experiment are field experiments. Shortly, it's somehow a lab experiment in the wild. So we still have a control group, and we are still testing one variable and by changing another variable. But now we have an uncontrolled environment. So basically what we were doing in the lab, now we are doing it outside. Temperature is not really fixed. We have some kind of wind, some kind of moisture by the air, things like this. The next type of experiment is the so-called natural experiment, and that's what usually most of the people in natural sciences are conducting, especially in the geosciences where I come from. And we don't have a control group, and what we try to understand the system by collecting observations from the system. We cannot really directly access the system to an extent like we can do it in a lab. In a lab, we control everything. In a natural experiment, we cannot control everything. But we can try to keep some variables constant while changing other variables. So we can see something. And that's what usually is done when we are in the geosciences or other ones. We are watching volcanoes. We know what goes inside. We're watching earthquakes or seismic activity. Some of them we can create artificially, and we know what we are giving inside. We know what comes out, and we know something about which is in there. And when we change the environment, when we change the lithology, when we go on other places, we can learn something about the lithology in there. And of course, we have an uncontrolled environment because we're not in a lab anymore. And the fourth kind, which is not an experiment, it's a so-called observational study. In observational study, we don't manipulate the system. We don't have this factor we are manipulating from the Wikipedia definition. We're just recording. We're recording the input and we are recording the outcome. But we can absolutely not access the system itself, whatever the system is. May it be a volcano, the inner core of the Earth, the universe, planets, whatever. So it's kind of a black box model. We know what goes in, we know what comes out, but we have no idea what happens in between, and we have to figure this out somehow. So on the next slide, I want to give you some examples for archaeological research, which might happen for this different kind of experiments. So for the lab experiment, for instance, we can test for high temperature properties of clays. We can go to a pottery kiln, we can have tablets of identical size, and we can fire them to different temperatures and then analyze them. And then we will see what happens when the temperature is different, but the atmosphere in the kiln was the same, and the size and the material of the clay tablets were the same. So everything is constrained except for the temperature. And from the temperature, we can get ideas about changes in the mineralogy and things like this. The same as like Sri showed last time for microorganisms, although it's really difficult to let them grow in the lab. To some extent it's possible, and then you can also constrain everything and maybe change the lithology or change the chemistry of the fluid, of the atmosphere, whatever. And for the field experiments, and archaeology experiments are a bit more large scale, at least the ones I was able to think of. There were some experiments where they tried to simulate slash and burn agriculture in Middle Europe. So they had a piece of forest and then they burned down some wood, some trees, and made agriculture there, and then moved to the next spot to simulate how it was back in the Neolithic, or the experiment was aimed for the Neolithic times. And this we can compare to normal agriculture like we do it today, without, of course, without without the fertilizers and everything, but without the slash and burn agriculture, just using a field like it is. And you can see differences in between. And we are in an open environment, and more or less everything else is constrained as far as it is except that on one field we are using the field as it is, on the other one we are slash and burn every year the field and create a new field. The same with forest pasture. You can look how animals develop when they are fed in the forest, for instance pigs, or on a normal pasture, normal food. The same with fire setting in the mining. It's also something where you can control it quite well, although it's maybe a bit more difficult because the control group, you have stone, which is not changing. And also in the conservation sciences, we can take our microorganisms, we can go outside, have stones there, can have a look on how they are growing there and the like. So for the natural experiment, that's what that's my background for melting experiments and kiln firing of ceramics, like really building a pottery kiln and firing it in there, not an electric one, but with wood, like in the old days. That's what what comes in mind. And as I said, that's the biggest part, the biggest type of experimental in the natural sciences. So that's basically what most people mean when they use the word experiment in natural scientific publications. And on the last part, observational study is basically everything when we are trying to explain the black box archaeological record by using archaeological materials. We can get observations from the material. We have probably an idea what was in there when we look on metal artifacts. We know, okay, from metallography, it was heated, it was treated, annealed, whatever. And we can have a look on how's the hardness, how does it look like, and all those things. But we don't really know what happened in between. And the same as with geophysical prospection, like we have after my talk today. We are measuring for geomagnetics. We are measuring the magnetic field of the Earth and the distortions, but we don't really we know nothing about the area of what is below the surface. That's why we are doing it. So we know what comes in, we know what comes out, but we have absolutely no influence on what is in the surface, under the surface, and this we have to figure out. We have to model from the signals we get. So on the next slide, I want to give you some ideas or some photos what might be experimental archaeology, because experimental archaeology should be within these three kinds. It shouldn't be an observational study because that's not an experiment, but it should be one of these three different kinds. And okay, Sergio, just tell me when you are clicking the next picture.
Sure.
Okay, so now you can see some warriors running. It's really just to give you, to think about what you see there. Is it experimental archaeology or not? Okay. Are you on the next one?
Yes, yes. This is experimental archaeology.
Yeah, okay. Just You're already, okay, I have the screen now. You're already much further than I thought. Okay, so you saw the pictures, and some of them were looking like this could be experimental archaeology. Some of them you saw there's a crucible in there or something which looks quite modern, which is probably not experimental archaeology. So for Wikipedia, experimental archaeology is also called experimental archaeology or experiential archaeology, and is a field of study which attempts to generate and test archaeological hypotheses, usually by replicating or approximating the feasibility of ancient cultures performing various tasks or feats. But when we look into the experimental archaeological literature and how they define experiments, we see that, for instance, after Cunningham and colleagues, that they make a difference between archaeological experiments, which have a specific research question, which are reproducible, which are connected with an archaeological record, and the archaeological experience, which is, according to the Wikipedia definition, the same. But the archaeological experience doesn't have a research question. It can be used for pre or pilot studies of actual experiments and could be used to identify the important parameters. And it's equally important. It's not inferior of experiments, but it's just another kind. It might change, for instance, how we understand the material culture when we have it in our hands, try to process whatever we want to do. If we want to make a vessel, or if we want to smith something, or whatever. It's basically, it's a bit playing around, but it's playing around with sense. And it's important, but it's not an experiment. It's not scientific in this regard. So, okay. So yeah, on the other side, you can see the diagram. And when you look at it, we start from archaeological data. We build a hypothesis. So we have a specific research question. We are thinking about what we want to test about the hypothesis. We are designing our experiment. We are performing it. We have the data. We compare the data with the archaeological record. We draw our conclusions based on logical reasoning. And we are testing our hypotheses. And then we can accept or reject the hypothesis and can start to make new experiments which are more detailed and more focused on some certain aspects or the like. So that's basically the scientific method, and that's how it should be. And in experimental archaeology, one of the big prejudices is that it has to be authentic. And what is authentic? And here I would like to cite Outram or Outram in 2005 in his article from World Archaeology, where he said that such experiments, of course, investigate activities that might have happened in the past using the methods and material that would have actually been available. It doesn't make sense to use modern furnace with gas or oil or something like this to smelt metal and say it's prehistoric metal smelting. That absolutely makes no sense. But the important thing is that it's not to say that all materials and methods need to be authentic in experimental archaeology, but certainly those pertinent to the hypotheses. So if we want to do a smelting experiment, it doesn't mean that we are not allowed to wear protection gloves or something like this because it's modern material. Definitely not. And that's a big difference. That's something we encounter quite often, that people more into living history say, yeah, you have to be the clothing like this because otherwise it's not authentic and something like this. But experimental archaeology, it's a bit different. So when is an archaeological experiment scientific? I said it has to be a goal and it has to be solution oriented. So we have an hypothesis and we want to falsify or verify this hypothesis. That's our goal. And experimenting is not learning by doing. So we know what we are doing. And in the best case, it's the last point, we have already some kind of skill and we're not starting at zero with our skills. An experiment has to correctly model the archaeological record. That's something we want to recreate it. It has to be measurable. and it has to be repeatable. That's basically the characteristics of part of the definition of an experiment, as we heard at the beginning. And it has to be professional, planned, and supervised. And the 7 basic activities, they are coming later in the text from Kelterborn, but it's not of interest for this part of the talk. You can, Sergio will put links for the full references for all literature in the video description when he's uploading it later. So measure repeatable means we have some proper documentation, something which is often missing in things which are called archaeological experiments. Okay, you can do the next one. And the, yeah, Sergio, yeah, exactly, thanks. And the somehow experience seems to be a factor, but how do we want to document experience? I mean, experience is something we make, something we feel, or something like this. It's nothing you can, it's not easy, but there are 2 different kinds. The first one is so-called explicit knowledge. So it's everything we can make explicit. We can explain it, we can write it down, we can document it, as you can see on the photo. The other part is that's the difficult part, is the tacit knowledge. It starts when you say, yeah, it feels like it should be done now, or it feels like there was enough time, that the ore was in the furnace and we can add some more ore. When someone says, yeah, you simply know, but cannot really explain it. It's more about a feeling than it's really knowledge. And that's what makes craftsmen so special, because they have a huge tacit knowledge, and often it's this what is lost, and also it's this what is lost in the archaeological record, even if we have bunches of literature from Roman times or something like this. And we also have to keep in mind that what we are recording today, like the temperature, furnace atmospheres, clay composition, whatever it is, it does not necessarily mean that it was important for them. We should not forget they didn't have the instrumentation. They were not able to measure temperature. They were able to say it's hot. And based on the color of the flame, they were able to see it's really hot. And if the flame, for instance, was white, they were able to say, okay, now it's hot enough. But they didn't care if it's 1,000 degree or 1,020 degree or something like this. So we are on a different resolution. We are on a different, we come from a different end to the whole thing, because we are trained as scientists. And nevertheless, it's important to record these things, because we have to make them explicit for the ones after it. It comes about the reproducibility and repeatability. So the benefits for archaeological, for experimental archaeology, for archaeometry, sometimes the archaeological record is not good enough. And I will give you 4 examples. Yeah. For instance, if we need the connection between finds, if we need to know how they relate to each other, an archaeological record is usually unknown. We find them next to each other, but we cannot know if exactly this ore was used to produce exactly this piece of metal, for instance, or that exactly this pile of clay was used to produce this kind of pottery. And in between, in an archaeological experiment, because we conduct it, we always know it. If we don't know it, we made a bad job in documentation. The next one is the influencing parameters. In an archaeological record, we can know more or less. From metallography, we can know it was annealed. It was probably annealed at around this temperature or something like this. For pottery, we know it was an oxidative or it was a reducing firing. But in archaeological experiments, we can know them. And more important, we can even measure them. We know exactly how, for instance, was the furnace atmosphere, how was the temperature, how oxidizing was it, where was it oxidizing, and something like this. In archaeological record, we always have to take into account post-deposition and alteration, or for metals, usually it's called corrosion, but it's also suffering, also ceramics are suffering from it, changing the chemical composition. For glass, it's very obvious with this iridescent layer around glass. In an archaeological experiment, we don't have it, because we are creating the material right now. And the repeatability is also not given in archaeological record, because we don't know. Each record is more, or each feature is more or less unique and probably were made by the same, but we cannot know if they were really by the same way. In archaeological experiment, we can ensure that we have to ensure actually that it's different. And the other benefit is that sometimes lab people are not that aware about how it was really. Like I said before, we are coming from a different direction. And past people didn't have our scientific instrumentation. So if you're standing out there trying to fire pottery, trying to make a piece of, trying to make a vessel, it might give you a lot to understand what is important about the technology, what are really the matters. So I would like to elaborate on these points a bit further on a case study. It's experiments we conducted by ourselves 2 years ago. And our hypothesis was whether copper isotopes fractionate during prehistoric smelting of copper sulfides or not. If they are fractionating, this might give information about the parameters. Copper isotopes are sensible to changes in the temperature, in the atmosphere, so if it's a bit more reducing or a bit more oxidizing in the furnace and things like this. If they're not changing, because there are really high temperatures where the effect might become really, really small, we can continue to use them to trace down the exploitation history of ore deposits. Because in the environment, when an ore deposit is interacting with meteoric water, with rain and environment and everything, fractionation happens there. And we can use this information to trace on the exploitation history of the ore deposit, but we can use it only if we know that during smelting nothing happens, because this will obscure our information from the deposit. And there were no previous studies on this topic. There was nothing to directly say, okay, this was already done, we know it should be like this and this. So what we had to do, we needed to know all the materials and their relation to each other. We needed to know that exactly this ore, this charcoal, or this wood was used and to produce this medi, and from the medi to produce the copper. And the process chain copper production with sulfides is quite complex. You have to roast it, you have to smelt it, you have the medi, you have to roast the medi again, you have to smelt it again. That's might quite a lot. And during all these steps, fractionation might occur. So it's nothing where you can easily say, yeah, I use the archaeological record, because you don't really know from which step is it. Yeah, okay, you know the copper must be from the last step, but in between, what happens between the ore and the copper is really difficult to see or to deal with. And the other thing is post-depositional alteration. As I said, copper isotopes and ore deposits are interacting with the environment. And of course, they do so when they're in the soil of an archaeological in an archaeological site. It's more or less the same process. So also there might something happen, and we have no idea how it affects the object when we want to analyze it. So it's also something to get information we cannot really deal with. We have to exclude. Also, the process conditions must be known, because, as I said, temperature is of importance, the furnace atmosphere is of importance, so we have to control it somehow. This is something we cannot reconstruct from the archaeological record. And we need to know to correlate it later with the analytical data. So experiments were necessary and not an observational study. And our solution was to use archaeological experiments and not an archaeological material. The next question was, do we want to have controlled conditions, or do we want to have field conditions? Or to put it a bit different, do we want to have really good, well-constrained data, or do we want to have authentic data? On the next slide, yeah, you can see on the lab conditions, one time space. Yes, thank you. Lab conditions, I will start with the pros on the bottom, but I will start with it. We can constrain experiments really, really well. We have furnaces, like lab furnaces, where we can exactly say we want to have this temperature, we want to have this atmosphere. It's really producible. If we homogenize our ores really well, we can even reproduce this more or less. So we have really good data. The problem is copper sulfides might be a bit nasty. There might be some foul ore in it. Foul ore contains lead, zinc, sometimes arsenic or antimony. And lead, zinc, and also arsenic are somehow volatile. And if we are at 1200 degrees, some of them will also evaporate. And you don't want to have them in your lab, not only because for your own safety, probably mostly because of this, but also you would contaminate most of the equipment. And it's really, really difficult and more or less impossible to get rid of lead and zinc once it is in the air condition or something, and like it's no. So even if you wanted to do lab conditions, it would have been really difficult to find a suitable lab. The other thing is labs are spatially constrained. There are different behaviors in a smaller furnace, like 10 centimeter are different than 30 centimeters of a circle or something. You have a different surface. You have a higher surface and smaller, or the ratio between surface and volume is for small objects is higher. So you have higher heat losses. You have to deal with homogeneity within the furnace. This might be given in lab conditions, but when you use a bellow, an ancient technology, you definitely didn't have a constant homogeneous atmosphere within the furnace. And the third thing is lab safety. I mean, lab safety is important, but sometimes it's also quite hampering. And if you have furnaces which are only allowed to operate when they are closed, you cannot really interact with the furnace, although you probably need to. And things like this, sometimes it becomes really difficult. So on the other hand, we have field conditions. Field conditions mean we go out, we build our furnace, more or less like they did in ancient times, and we conduct our smelting experiments there. The problem is we have really badly constrained experiments. There is wind, there are temperature changes, we have so many factors we cannot control just from the environment. Because also of them we have low reproducibility. And they are much more expensive and they need a lot of effort. So for the experiments we conducted, we had half a year preparation for basically 4 weeks of experiments. And it was fun, but it was also a lot of efforts, a lot of work which needed to be done before. And even during the 4 weeks of experiments, more than half of the time was grinding and crushing, smelting products and ores and not really doing smelting. So it's really a lot of time you spend just to get your results, and it would be much easier in a lab. The other difficult thing, especially when you want to do smelting experiments with sulfides, which are stinky when you burn them and not really healthy to a larger extent and everything, it's really difficult to find a suitable place. It's difficult to find a place where you have enough space around that you can operate at 1200 degrees Celsius without having fear of setting everything on fire, without forests around, at least in Middle Europe, and everything like that. So that's also something, there are not that many places. There are special labs like the Laboratory for Experimental Archaeology in Main from the AGZM. There are other places in France I know about. There are some villages and museums for experimental archaeology in other European countries I heard of, but they're really constrained. So you have to be flexible in the place, but you also have to organize a lot to bring all the materials towards the place. It's not like you go in the lab and you order your material and you can start. And the last contra is the skill of the experimenters. I mean, I know how to operate in a lab. I know how to operate in the furnace and something, in a lab furnace or something like this, but I was never doing smelting before. So you have to find expert in this area, or you have to do some experiences in archaeology, like and getting a feeling how to smelt ore. And of course, you don't want to have this kind of try and error too much, because then it becomes even more expensive without really having an outcome for the project. So that's also something. But on the other hand, you have a much better authenticity of the materials. I mean, we cannot say it was exactly done like this, but we can say probably it was done like this. We have a full-scale operation. So many things I would have never thought about when I was just having the material in the lab, having the lab with all the well-defined environment, not need to think about how to operate a bellow, if different kind of smeltings, different kind of operations of the bellow or something like this. So it's really, you get a much better idea about the technology. So when when we designed the experiments, we had to clarify some points. The first one is, what is the process we want to reconstruct? What is a suitable process? We didn't want it to start from scratch. We wanted to have something where we can compare towards it. So we needed a good archaeological record. We needed a good documentation. So it's not that we have a good archaeological records from the beginning of the 20th century or something like this, but something more modern, where we can ensure that it was well documented and the information is reliable and have good pictures to reconstruct the furnaces from. There should be, in the best case, there should be some previous experimental work, so we know at least somehow what we have to take care of, how we should operate a furnace and things like this. And there should also be a good amount of scientific work, because then we know on the archaeological material, because then we compare our material to the archaeological material and can say, okay, yeah, the microstructures fit, so we were in a good window of the furnace conditions or something like. So we know that we are close to the archaeological record. Maybe it was not the process they used, but at least we are creating more or less the same materials, so the process should be comparable. The next question was, what do we have to document? Which are the parameters we have to think about? And there we have to think about what influences the copper isotopes. As I said, the furnace atmosphere and the temperature. There might also be other ones. We have to think about sources of copper. Copper is not only in the ore, it's in everything. And even if it's tiny amounts in the wood, if we burn 250 kilograms of wood in one smelting operation, it might have some influence, because also tiny amounts can make up a good amount in the end. So we had to thought about these parameters, but we also had to think about which parameters are impacting the smelting process as such. We cannot just think about the copper isotope fractionation. We also have to do successful smelting, and somehow they relate to each other. So we have to think about them, and we have to think about which kind of which parameters we can constrain. So which one we can keep constant, and which we can measure. You cannot measure everything. For instance, it was, for us, we were not able to think about a method to measure the loss of copper due to vaporization during the furnace. The furnaces are operated from top, so you cannot put something like a roof where the copper will precipitate from the fume or something like this. It was just impossible. So we have to live with it, that we have a loss of copper we are not able to account of. And the same with the bellows and something like this. You cannot really constrain the amount of air given into the furnace, because the same person, we are not robots. When we are operating the bellows, we are doing all the time exactly the same. And you cannot sit there for 8 hours working on a bellow. So you have to change with other people. They are operating the bellow a bit differently. So there are also something in there which cannot be constrained, and we have to live with it, but we have to take it into account. The third point was the number of experiments. As I said before, we needed some training, so we had to get enough experiments that we can include some training. We also have to take into account that even if we are perfect persons, we might fail in experiments. We need a buffer for this. And of course, we want to have some repetitions on the one hand, to show it's repeatable, but on the other hand, also to exclude accidental behaviors we were facing because something weird was going on in the furnace and we didn't realize it, or there was something, yeah, just something we were not aware of. Like there was some remains from in the soil or in the furnace wall or something like this, which we overlooked or whatever happening, just in case to be on the safe side, because we knew we cannot go back to do more experiments afterwards. It was not just possible because the organization, the funding is the one which really limits funding and time, which really limits experiments, at least our experiments, because smelting experiments are really expensive. And so we were able, we had to get the funding, we had to show we are really needing these experiments and not doing them just because they are fun or something like this. And then we had to find the area and the accommodation. We had to find enough people because you cannot do a smelting experiment for a month with 3 people or something. Like you need much more people, and suitable materials, and also suitable equipment for documentation. You cannot use and recording. You cannot use just the thermocouple like you want to do for 1,200 degrees Celsius. You need some where you know that they don't melt during this procedure and that they are stable under reducing conditions and something like this. And of course, the documentation strategy must be suitable, because probably different people from the volunteers will do the documentation as well. And so it has to be comparable what they record and everything. So it was a lot of things, and a lot of things where I was able to take what I learned in the lab to put it outside, like for instance, documentation, to have a good documentation. I used more labs, tried to implement lab standards, but other things I had to go with what were the experiences of the previous experimenters. One of our colleagues already did some smelting experiments, and she taught me a lot, and we talked a lot about the parameters and what to take into account and everything. So it was really a give and take, or was really to working together and not just using experimental archaeology. Okay, so yeah, for all the fun part, which is doing the experiments, and if you want to know more about the case study, we made a documentation on the blog. It's called copper-smelting.com. I don't want to show the pictures here, just to be on the really safe side concerning copyright, and also the experiments itself. It was done like experimental archaeology, and doing the experiments is nothing related to archaeometry, and the analysis is just the analysis, it's archaeometry. So they're both are splitting somehow again. And afterwards you have the results, and then you can think about, and that's basically the circle. You have the archaeological record, which is interacting with experimental archaeology and archaeometry. Both of them want to understand the archaeological record better. And archaeometry can profit from experimental archaeology and using the material and data produced during archaeological experiments, but also experimental archaeology can profit from archaeometry by using the analytical results. So it's really a give and take. It's not next to each other. And next. Yeah, so archaeometry can help to design good archaeological experiments. And if we find something we never found before, we have no idea how it was produced, for instance, it might be even possible that without archaeometry, the experimental archaeology wouldn't be possible, because we have absolutely no idea where to start. And we cannot just start by, okay, we can start by playing around, but we cannot know if this actually what happens. So we need some idea about, for instance, the metal object, how it was made or something like this, before we can start to reconstruct the technology on a more practical base. On the other hand, archaeological experiments can provide tailor-made material, like in our study, and they really help to understand ancient technologies. And before I finish, I have one last thought for you. When we go back to the definition of archaeometry or archaeological science, is the application of scientific techniques to the analysis of archaeological materials. So what we are creating are modern materials. Can we still call it archaeometry then, what we are doing with the experimental materials? And with this, I would like to thank you. I saw that there's already one question from one guy in
Ole. From Ole.
Yeah, okay. Yeah, so that's it really depends. I wouldn't say it's experimental archaeology, because if you use modern equipment, if you really use modern equipment like they're doing it in a factory or something like this, then it's not really connected to the archaeological record anymore. So this part is missing. Of course, you can replicate the metal composition or something like this, but it's more a lab experiment. I mean, you can also do smelting. You can go in a lab and have a small smelting furnace. We did it once. We used an induction furnace, like a magnetic field, to smelt malachite for more or less the same reason. But it's not really connected to the archaeological record anymore. So I would say it's lab experiments for archaeological or archaeometric research questions, but it's not really experimental archaeology anymore.
Okay, I have a couple questions before we go on, because I can see there are some more questions. I would like to thank you a lot, Thomas, for the interesting talk. This is a very nice topic. And okay, I have one question. It's about the ore sourcing and the flux, because you're trying to recreate something like it was done several years ago. And the mines, of course, they change it through the course of time. And how do you sample for the ore to try to get as close as possible for the ones they use? Do you do that, and also for the flux?
Well, for the ore, we were in a really, really lucky position. We decided to recreate the ore smelting they did in the early Bronze Age in the Mitterberg region in the Eastern Alps, because it's really well documented. And we were in the really lucky condition that Erika Henning, who supported us a lot during the experiments, who already did experiments for her PhD thesis, had 150 kilograms of the ore from the mine, which was identified as the main lode of the copper source for the prehistoric people in their basement. So basically, we had 150 kilograms of the original ore, which is just awesome and really.
Yeah, we were very lucky.
Yeah, exactly. It's nothing you can expect.
Okay.
If you're not in this lucky situation, you can check. I mean, there were remains of the ore found. What we find usually on the waste piles is the stuff they didn't want it to use for smelting, because it was not rich enough, not pure enough, and they just discarded it. But from this, you know the mineralogy, you know the composition, you know if there were chalcopyrite or fall ores or a mixture of it in there, because you still have traces. From the archaeological material, you can also know what ended up in there. That's another way to see from the trace elements which ores were used. If you have arsenic or antimony in it, it has to be fall ore, at least from the really major copper ores. And from the archaeological record, when you know the furnace and the dimensions of the furnace, you can somehow estimate what were they able to use. So how rich had the ore to be, what needed to be the grade of the ore. And with this, you can reconstruct somehow, and then you can look for, there are vendors for ore and for mineral collectors and things like this. And then you can try to can contact them and can look what kind of ore they can organize from different deposits. Actually, it turned out it's really difficult to go to a mine, because when they want to sell you at least 100 tons or something like this. So basically, beyond anything.
Of course.
And so it's not that good enough, but it's the closest we can get. So we have to deal with it. I mean, and archaeology is always reconstructing, and
yes, of
that's
course.
also. And the other thing with the flux, it's the same. You can use chemical information. For instance, when your slag has a lot of calcium, you know, they probably use lime as a flux or something like this. But in prehistoric smelting, at least where I'm now working on in Lebanon, but also the experiments we created there for the Mitterberg region, the ores they used are mostly self-fluxing. They have a proper amount of iron and enough, or most time, more than enough silica in there that the slag is forming themselves without the necessity to create flux and to create.
And this will lead me to kind of my next question, and it's when you have missing information, when you're trying to reconstruct, what do you do to fill in the gap? So do you assume the closest possible to what is reasonable from that period you're trying to recreate the experiment? And how is that choice done if you have to do so? I have no idea.
Yeah, what we had to do for the next step when we had the MADI, the problem with the Mitterberg process is we have the furnaces, but we have no idea how they process the MADI further on to create copper out of it. And what you have to do in these cases, you can just look in ethnoarchaeological records or on other sites where they probably have this. We have some features which are a bit suspicious, but they are not really convincing. And so you can try. Again, you have the analysis, you know what MADI looks like, and probably you see changes in there from different steps or something like this. But yeah, try to get as close as possible what is reasonable for you. It's in the end, it's science, and it's about building and verifying, falsifying hypotheses. So if you're giving good reason why you did it, then people can follow you, can think about it, can say, oh, I disagree. I would do my own experiments because I think what you did is probably not bullshit, but it's far off the reality. But still, they are able to deal with it. That's why documentation is so important, and not only documentation, but also giving a proper reasoning why you did the things that people afterwards can exactly do this and can evaluate it, and then you can say, yeah, it's like the question with the cognitive archaeology.
Yes. Yes, going back to the chat, we had one question from Yuri about the cognitive archaeology. Okay.
Yeah, it's a good idea. I don't know that much about cognitive archaeology, but what I was really trying to do is to put aside my scientific knowledge to an extent that it's not influencing when operating the furnace. It's not about standing there and like a slave every 15 minutes adding the next batch of ore or something like this. It's a bit more difficult, but you have to get a feeling for it, because the furnace is operating every time a bit different. You have different wind going into the furnace, giving more air than you get from the bellows and things like this. So that's really something, yeah, you have to feel about. You have to create and to gain this tested knowledge yourself. And it's why I was saying several times that it's, from my experience, more or less the best idea to really understand how it worked and what are the important factors. It's not important that the furnace was 1,200 degrees or something. It was important that there was a green flame, for instance. And these are things you probably might learn from literature, but you really understand them, I would say, when you just experience them. So I don't know if it's answering the question, because I'm not that sure what cognitive archaeology exactly means, but hopefully it does. And yeah, and One, if you're really interested in the composition, yeah, then of course you can do the experiments, but I would not call it experimental archaeology anymore. It's an experiment for archaeology, but it's not an archaeological experiment, because you're just off the archaeological record. Let's put it this way.
Yeah, okay. If there are any more questions, please type in the chat. If not, we will proceed with our next speaker. And thank you so much, Thomas, once again.
Yeah,
Okay.
welcome.
And we are going to be off for the next 5 or so minutes with our next speaker. And see you soon. Thank you so much once again, Thomas.
You're welcome. Thank you.
See you soon. Hello everyone, we are back. About the last talk, which I forgot to mention, all the references that Thomas mentioned, we are going to add all the links to the final cut of the video, so you can access everything on the video description. Everything is going to be there. I'm connected with Yuri here. Good afternoon, Yuri. Good morning in the case for you.
Yeah, well, it's afternoon already. Like it's midday.
Okay, so we are
So
bothering
we're all
you in your
good.
lunchtime. Perfect.
Nah, no, not at
So,
all. Thanks so much
uh,
for the invitation.
well, thank you for accepting and joining us. If I hope you can all hear us. And Yuri, he's a bachelor in history from the Federal University of Uberlândia, and he's a master in science and technology for the conservation of cultural heritage from Thessaloniki University. He is a member of was a member of the Ashmat consortium, where we have these traveling around, so we have a diploma from everywhere. He's a dear colleague, and once again, thank you so much for being here and giving us this talk about archaeometry and archaeomagnetism dating.
You could just say I'm an ArcMat survival.
Yeah, either that. Okay.
Kidding. It was an amazing experience.
So.
All right. So
Okay.
shall we get started?
Yes.
So
Thank you very
then,
much.
good afternoon, guys. Thank you so much for the invitation. So I'll be talking a little bit about my contribution for archaeomagnetic dating, and I'll talk about as well a little bit of archaeometry, specifically petrography and spectroscopy, and how that contributed for archaeomagnetic dating. So what I'm about to say, it's nothing new. It's basically the potential of interdisciplinary studies. Basically, we'll be focused on pottery as our sample of analysis. It's a further step for modern archaeologists to get more and more used to archaeometry and other kind of techniques. Even though archaeomagnetic dating and archaeomagnetic studies in general is not my main focus, I decided to do this presentation focusing more on that because it's a bit more unusual. When I normally tell people about it, they're like, what kind of sorcery is this? But no, it's all scientific. So as you know, archaeometry, I would say, is the use of material science technique on archaeological materials as well on cultural heritage. I find it interesting, the speech of Thomas, but I would say it's like material science, because of course archaeology itself, it's science, but it's not so much material science. That's where archaeometry play through and just it's just like an alloy of many different kind of sciences. So the samples are from the Hellenistic period, and what is interesting that you should know about, an interesting fact that you should know about these samples is that during the Hellenistic period, there was a massive pottery production. Until then, nothing seemed like this before because the pottery was like, there was a specific type of pottery for decoration that would like to simulate the ones that the royalty used, etc. I'll give you guys as well a brief geological and archaeological introduction / evidence of these ceramic productions. And all the samples are from northern Greece, specifically Pella, Tassos, and Samothrace. All right, so here we have a beautiful map done by myself on Paint. So basically, let's start from west to east. We have this red star is Pella, where used to be the capital of the Kingdom of Macedonia, birthplace of a certain Alexander the Great. I don't know if you ever heard about him. And what you need to know about the geological condition of this area is that it's very alluvial. It's characterized by many rivers, even especially rivers that are already dried. So most of the main characteristic of the geology is that it's rich on sediments. As we go to the east, we have Tassos. Tassos is a fairly large island from Greece, very close to Hokkaido, where whoever lived in Greece know how beautiful it is. And Tassos is interesting because it was since ancient times. It's characterized by massive amphora production, and it was not difficult to trace those samples because, as you may probably know, as an archaeological fact, amphoras normally have a stamp on it, so you have an easier time to find out which workshop produced these samples. And also Tassos was very, well known for the production of marble figures, marble architectures, and so on. So the geomorphology of Tassos is majorly characterized by metamorphic rocks, especially marbles. One thing I forgot to tell about Pella is that the samples were found within the kilns. So during the 70s and the 80s, while people were digging the samples, they found them inside the kilns. So this is an archaeological evidence that these samples were produced locally. I don't think somebody would just put samples from other places inside the kiln just to make fun of archaeologists in the future. No, that's definitely not the case. And further east, specifically northeast of Samothrace, of Greece, we have Samothrace. And Samothrace is an island characterized by both sediments and volcanic rocks. And it's an island well known by its religion. It's like a spiritual place. There are many temples dedicated to many different goddesses. As you can see, the statue of Nike, that the goddess of victory, you probably seen this or heard about it at least. It was found in Samothrace, just to give you an idea. Not all of the samples were found within kilns in Samothrace, but some were, and their morphology are very similar. All right, so the major techniques that we used was ceramic petrography, that basically you made a thin section from the ceramics, and you can have like an optical idea about what is present within your sample. Compared to spectroscopy techniques, is like a much wider sense, but it's interesting because it's low cost and also gives you some direction on what kind of approach you should do with other techniques. That's one of the major points about archaeometry. You should always consider using multiple techniques so they can complement on data with each other. As you can see on the top figure, we have one sample from Pella, and you can see that there's this white stuff around some of the porosity of the ceramics. These, some people could say that these are from calcareous clay, but actually it's penetrated from the soil. Basically, the soil had some calcite. We call these secondary lines or hypocoating of calcite. These are like impurities. It's not from the raw material, and that's an information you can already get from ceramic petrography. Basically, we get the techniques from petrography itself, which normally deals with rock, but many archaeologists adapted for ceramic. Anyway, we have scan electron microscopy to give a further characterization of the, not only identifying more minerals, but also the composition and the clay characterization. As you can see, these two pictures in the middle. The one from the left is a picture from the outer core, and the one on the right is from the inner core, because some of our samples has difference in color, and normally you can attribute that to difference in firing. Basically, it was on a certain condition that not the whole vessel got to a maximum firing condition. We also did, for further mineralogical identification and to estimate the firing condition, we use XRD. And as you can see, this specific spectra on the very bottom, this huge peak is due to the calcite contamination that I explained before. But these two in red, the thermomagnetic analysis hysteresis loop, are basically the main techniques to check if the samples are suitable for archaeomagnetic dating eventually. Because some samples are from the same places, like from Pella, but some were useful for magnetic dating, like suitable, and some were not. So I basically assisted my supervisors, who is a geophysicist, to check it out, the composition, if maybe something on the composition could be the problem, to check the suitability of these samples, essentially. All right, so let's talk about magnets a little bit. So the historical information, as you know, there's this rock called magnetite, which is basically our daily life magnet, the magnet that we have on our fridges and so. But the Greeks were the very first one to actually track record about these. And it's called magnetite because most of them were found in the city of Magnesia, in a Greek colony in the Near East. But as well in China, in many other places, we should be careful of not being anachronic and also check that things happen in many different parts of the world in many different times. Like the Chinese were not in touch with the Greeks, but they also registered like these compass basically that you see in this picture. All right, so let's talk a little bit about the Earth magnetic field or the geomagnetic field, because that's the main point of archaeomagnetic dating. Um, it's not entirely sure how our magnetic field, the magnetic field of Earth, is generated, but it's definitely related to the interactions between the inner core and the outer core of our planet. Basically, they're very rich on iron, sulfur, and nickel, and the constant freezing and expansion of our core generates many different magnetic fields that over thousands of years go through the lower mantle, which is basically solid, so it takes a while, and then generate our external magnetic field, the one that we're more used to, the one that people use to improve our GPS and so on and so forth. So first, let's talk about paleomagnetism, which deals with the study of Earth's magnetic field variation during geological times. So it's a much broader timeline, let's say. Now, archaeomagnetism we're tracking just for a few thousands of years, so basically during human existence. So it's a branch of paleomagnetism which studied the variation of the geomagnetic field during the historical and prehistorical periods. So basically, in a very simple way, Earth is basically a giant magnet, and as you know, every magnet has a magnetic field, and the North Pole attracts to the South Pole, and while that happens, it creates a magnetic field. And what's the major point of archaeomagnetic dating? Basically, clay products such as ceramics, bricks, and so on and so forth, which are rich of ferromagnetic minerals. The point that you burn them as you produce them, those minerals register the current magnetic field of the time, because our magnetic field changes over time, both due to how our core interacts and also due to what we call sun wind, which is basically ions particles coming from the sun that just interacted with our magnetic shield. So the point is our magnetic field changes, and as it changes, we can use this for our advantage as a dating technique. So here we have the suitable materials. Normally when we talk about pottery, we think about vessels at first, but we also have bricks. We also have the kilns from the kilns walls, basically, which are also made of pottery. And they're interesting because they're very, well, pottery is definitely one of the samples that you find in much larger scales compared to other artifacts, because it's very resistant over time, and it's applicable at any type of permanent and undisplaceable fire structure. So it's not only ceramics, can be bath tiles, it can be furnace, the kilns. It's not, you could use rocks, but then we're talking about paleomagnetism, because rocks were formated way before any human, basically. But for a human context, normally rocks are not very interesting. And as for metal artifacts, its structure and its fragile condition also is not very interesting, and also the grains and the quantity of metals it will not be interesting for the readings of the equipments, essentially. All right, so let's talk a little bit about archaeomagnetic dating itself. So the study of baked clays based on the principle of well-fired objects structured recorded the magnetic field of the Earth during their firing and subsequent cooling. Yes, the cooling also helps on this process of registering the magnetic field. So the principles of this method, the method of archaeomagnetism, is based on the fact that magnetic minerals, irons, and iron oxides contained in clay-lined archaeological features such as kilns, hearths, furnace, burned walls and floors, or other fire structures acquired a thermal-remnant magnetization. So this is like a fancy word of what I said. Basically, this thermal-magnetic remnant, it's like the register, how it's registered the magnetic field of that time, let's say. At the time, and they were heated and subsequently cooled above the so-called Curie temperatures. These are all technical terms, so don't worry about it so far. The characteristic of each mineral. If the filters are not reheated to higher temperatures, the direction and strength of the Earth's magnetic field at the time they were cooled is locked in, quote unquote, and can then be measured in laboratory. Therefore, the materials magnetized at the same time in the same region will normally have identical directions, and the intensity of geomagnetic field would also be the same. And one important thing that I would like to establish about this is that sometimes accidents can happen. Let's suppose that in the Notre Dame cathedral, there were some ceramics from medieval times, let's suppose. But due to that firing incident, unfortunate, those samples will most likely not be suitable for magnetic dating because they were reheated. So they probably lost this magnetization. So yes, archaeomagnetic dating is like a destructible technique because it's necessary to do this heating process, and also you have to take some sample from it to use it on the spinner magnetic equipment. So the magnetic properties of pottery and baked clays are important to check the suitability of the material before doing the dating itself. And thermomagnetic analysis and hysteresis loops, once again, these techniques to check the suitability, to qualify and select samples for archaeomagnetic studies. So requires and limitations. The sample should have like a certain abundance of magnetic particles in the studied materials. Homogeneous materials, for example, bricks, potteries, which are made of homogeneous materials comprising small particles. When I say homogeneous, I mean like much more in a physical way than in a chemical way, like the way it's distributed. It's not so much like, oh, this is pure carbon. No, definitely not. Heating up the high temperatures accompanied with subsequent cooling that allows the recording of the geomagnetic field on the studied material. Studying in situ structures, so we can do the calibration, we can have a standard for it, and calculation of the geomagnetic field directional elements. All right, declination and inclination, sorry for these terms. Various environmental factors, for example, drought, humidity, underground water, and sometimes some archaeological facts, like if there's some records on a certain firing that happens, like an unintentional firing, as I said before, may affect the material and make it unsuitable for archaeomagnetic studies. Extremely fragile materials are difficult to sample and measure. Consolidation techniques can resolve this up to a certain degree. So yes, that's why ceramics can be very interesting. Here we have a very simple schematic. I don't think it showed it completely, but it was like a multiple arrows, basically showing our magnetic field and the geomagnetic field direction registered in the ceramic itself. Oh, nice. There you go. Oh, okay. You get it. Next. Oh, there you go. So yeah, so it's kind of like a way to track, the same way that you track how many minutes has passed. You kind of do the same, taking our own geomagnetic field compared to the one that passed in a very simple way, let's say. All right, so here we have basically all the equipment that you use. They are very bulky and they can consume a lot of energy. So you can put it all, please, like next, just to fill it out. All right. So the standard laboratory procedures, these are just like basically you're following some steps. So that machine that we saw was like a spinner magnetometer, and it's used for determination of the remnant vectors. These remnant vectors are related to the remnant magnetization of these samples. Magnetic stability and direction analysis are investigated by alternating the field and thermal demagnetization. That's why it's a thermomagnetic analysis. Now, this Tellier method is basically the whole calculation of the geomagnetic field and compare to our current magnetic field. But I'm not going through details because even I don't know all the details myself. It's very deep into physics and quite actually close to quantum physics. It's applied for the determination of the Asian magnetic field intensity, applying stringent criteria in the choice of the temperature interval for the regression line calculation. Normals of experiment of magnetic properties of the samples. Please, could you put a few more? Thank you. So just to give an idea of what kind of characteristic we get from this experiment. We get the magnetic viscosity, isothermal remnant magnetization. This one is the most important. Thermomagnetic curves, magnetic anisotropy, etc. And hysteresis measurement, which I'll try to talk a little bit about it. Please, next slide. All right. So the thermomagnetic analysis. So here we have some samples based on ceramics from Pale, well, one from Pale and one from Tassos. Basically, this red line is the heating curve of the sample that we do it to check if it's suitable for further analysis, archaeomagnetic analysis. So when the heating curve and the cooling curve, which is the blue one, they are very close, or they basically coincide, they are considered ideal samples. We call it reversible. Basically, it shows that the sample is not creating new minerals during the process, and all the magnetic the remnant magnetization of the samples are stable as well. Now, the one on the right, we have it's from a sample from Tassos. There is some difference, but it can still be worked on. Now, as for this one, we have a not reversible formation, so it's an unsuitable kind of sample. This one is from Samothrace. So as you can see, there's a huge difference between the heating curve and how suitable it is, the magnetic minerals within the sample. So it's basically susceptibility by temperature, this graphic. So right, this last one was an example of minerals being formed during this process. I think you went back, please. One more, yeah, there we go. Now, this is a very complicated factor, which is hysteresis loop, and it's to estimate the magnetic grains within the samples. The one on the right is like an ideal sample. What we call a single domain is basically the grains within the sample. They're all orientated to the same direction, which means it will not give you like a false idea of how it was the geomagnetic field of that time. So basically, you magnetize the sample, which is like this crescent curve, and when you demagnetize, if it follows a very similar pattern, then it's an ideal kind of sample. Now, the one on the right, it's another sample from Pele. We have two different curves, but from the same sample. The blue one is from the shell, basically from the outer core of our sample. Remember that there were differences in the structure of the ceramics and difference in color, like the core was more grayish, there were differences in firing. So basically we did the same, but with different areas from the sample. So as you can see, they have different readings in the hysteresis loop as well. So it's considered like a failed failure, like it's not an interesting sample to give further analysis for archaeomagnetic dating. Now this one from Tassos, you can see that it's not a perfect curve, but you can still work around it as a suitable sample, but carefully. All right, so the advantages of this method is that it's low cost, it's applicable for a variety of materials. As I said before, we're dealing with pottery, which is like what you'll find the most in archaeological sites. And most of these pottery are like shards that will not find a complete vessel. They will not, most likely not be displayed in museums. They have no decoration and such. They will be just stocked in box on the storage in the museum. So why not using these samples for dating? For intensity studies, the sample material does not have to be in situ. However, fabrication location should be known. For example, getting the sample from the kilns where the ceramic pots were burned, definitely. High dating accuracy for qualitative interpretation can be achieved due to the fact that more than one parameter are measured. So yeah, that's pretty much what I show with the thermomagnetic analysis and the hysteresis loops. You need more than one parameter, so you won't be lost. All right, disadvantages of this method. It's laborious, like it can be very long. I remember that it was so long that I honestly had to find some extra things to do while we waited for it. The accuracy of the method is affected by the accuracy of the secular variation curve. This is a very technical term, but it's basically how the spinner magnetometer measures the suitability of the material. And bureaucratic issues involved, sampling permits, etc., especially from where you're taking from, because again, it's destructible technique. So if you pretty much talk to the owners of these samples to give you permission to actually destroy them for this purpose, and maybe without much certainty that will be a success, because you have to do all these procedures to see if the samples are suitable. Yeah, it can be very difficult, especially in Italy. Like if you tell them that you want to destroy ceramic, they'll probably kill you. Next, please. All right, so here I have a few references. So if you want, I'll send you guys later, and I would just send it to Sergio as well. But I would recommend the most the works from Spataras well, nowadays she's a professor at University of Peloponnese, but she's doing a nice study on archaeomagnetic dating, and also Despina Kondopoulou, who was my supervisor back in the masters.
Okay.
And that's pretty much it. Thank you.
Thank you so much, Yuri. Thank you for the presentation, for the interesting topic, and very interesting technique. That's pretty unusual, I must say.
Yeah.
I myself never heard of that before.
Yeah.
And I will see if we have some questions in the chat. So, okay. Ola asked if the vessel used for cooking would still be suitable for this kind of study.
If the vessel used for cooking. Yes, because the problem is getting to a very high temperature, like the kind of temperature that he used to fabricate to produce these samples.
Yeah.
To bake it, yes. So cooking, no, it's not a problem, but now I don't know what kind of recipe you do that you need to reach the pot into like 400 degrees Celsius. I hope not, but yeah, cooking is can be used for sure.
Yeah, but even though if you reach such high temperatures, you would still be able to date. But maybe the last time they used that vessel, not the fabrication, but maybe. Am I right or not?
Yes. My point is, cooking does not affect the suitability of the material. Yeah.
Okay, you could still use, but you will get the date when it was last used.
Yes, because for the to release this remnant magnetization of these grains, you really need to heat it up the samples to like absurd point. Like your food will be burned, like it will be vaporized. So
yeah, it will be a very bad omelette or lasagna.
Oh, definitely.
Okay.
So yeah, I hope that makes sense.
I don't have any questions, but I really like the technique. It's rather new for me. I have seen that before, but never in depth or gave much thought about it, to be honest.
Mm-hmm.
But it's quite interesting about how you can use this information on the Earth magnetic field to date. You can do some kind of provenance. I was searching for the word. Some provenance studies with that, since the magnetic field changed direction, or is that too restrictive? Is it possible?
I believe it's very possible, because we have different fluxes of the magnetic field. Definitely, the thing is, you also you need to date first, and then you can find other parameters getting samples from this specific area. Let's suppose that I found a ceramic from Jordan, and then I will have to go to Jordan and also get some samples from there. And yeah, eventually, yes, indeed.
Okay, yeah, because one of the things was knowing the provenance to date. If you wanted to date that, you would need a provenance. That's why I came with that.
Yes.
Okay.
Yeah, just as a compliment, since you spoke about provenance, since you're doing also material analysis, you're doing petrography and as well as spectroscopy, you already get enough information to find the provenance of the materials. So, I mean, the archaeomagnetic measurements can do that as well, but I talk mostly about how it's dated. The other kind of archaeomagnetic measurements I'm not entirely familiar with.
Okay, so we have no more questions. Shri is thanking you. Well, and that's it. I apologize for some technical issues, because today I was not only the host but also the guy passing on the slides, because we had some technical difficulties with the plugin to grab the speaker's screen. And okay, I'm going to finish the the stream. And I will let you all know through the mailing list, as usual, about the next and upcoming talks. Okay, thank you so much for participating. Thank you all. Thank you, Yuri, once again for being
Thank
here.
you.
And see you
Thank
next
you all,
time.
guys. Have a nice day.
Bye.